Assalamualaikum warahmatullahi wabarakatuh. Okay, let's look at the one-dimensional heat equation where we will discuss two cases. The first one will be the case A, when both ends of the rod are kept at temperature 0 degrees C. And the next one is for case B, where both ends are insulated. Okay, so right now this is the equation for heat equation. Okay, the formula for the heat equation, which is UT of ST equal to K US X of XT, or can also be written as del U over del T equal to K del squared U over del X squared, where K is greater than 0. Okay, so this equation 1 occurs in the theory of heat flow. Okay, that is when heat is transferred by conduction in a rod or in a thin wire. Okay, right now we will consider what? Rod or thin wire. Okay, and the function UST here, okay, this is important for you to understand. The function UST represents the temperature at a point X along the rod at some time T. Okay, UST is actually the temperature. Okay, UST is the temperature. Okay, right now let me highlight it. Okay, so suppose that a thin circular rod of length L here, the length is L, from here to here. Okay, the length is L, and has a cross-sectional area. That means inside the rod, okay, across anywhere, cross-sectional area A, and coincides with the x-axis. That means here it coincides with the x-axis here. And on the interval 0 to L, the following assumptions are made. Okay, that means here, let's say this is x, this is x plus delta x. Okay, that means there is a change here, which we call delta x then. Okay, so the assumptions that are made are, okay, the first one, the flow of the heat within the rod here takes only in the x direction. That means it goes that way. Okay, it should go to the right. Okay, remember, it should go to the right from point of higher temperature to lower temperature. That's what it means. Okay, that means it will go from higher temperature to the lower temperature. Okay, and the lateral or curved space of the rod is insulated. That means the curve. Okay, the curve here, the cover of the rod. Okay, the lateral means the curved part is insulated. There is no heat escapes from the surface. Okay, and no heat is generated within the rod. Okay, next, the rod is homogeneous. That means that its mass per unit volume rho is a constant. Okay, the rho is constant, and the specific heat gamma and the thermal conductivity K kappa of the material of the rod are constants too. Okay, that means gamma and kappa are also constants. Therefore, the boundary conditions when it is case A, okay, means both ends of the rod are kept at a constant temperature of 0 degrees C. The boundary conditions are U0T is equal to 0 because we kept the initial temperature at 0. So here should be 0. Okay, equal to 0, and ULT is equal to 0. That means the end of the rod are also 0 degree. That's why ULT equal to 0. Okay, for T greater than or equal to 0. Of course, time should be positive. There is no negative in for time. Okay, and for the second case, case B, both ends of the rod are insulated. That means no heat flow through the ends, and the boundary conditions are del U del x 0T is equal to 0 and del U del x LT equal to 0. These are the difference. Okay, where del U del x is the rate of heat flow. Okay, that means it's insulated there. That's why we need to differentiate here. Okay, differentiate with respect to x. Okay, and then the other condition is the initial temperature. Okay, the initial temperature is given as Fx, and thus the initial condition is Ux not equal to Fx. Okay, for x between 0 to L, and please note too that the positive constant K is equal to kappa over gamma rho, and this is called as thermal diffusivity. Okay, and next, okay, the solution of the heat equation. We have this equation, right, for the heat equation. That means the first one, both ends are set at temperature 0 or insulated. The same goes here. Okay, that means at both ends. Okay, let U of xt equal to x of x, t of t. Okay, that means U xt is equal to x of x times t of t. Okay, the direction times the time. Okay, that will be the temperature. Okay, so by partial differentiation, utxt is equal to x of x t prime t. Of course, because we differentiate with respect to t. Okay, that means the function in x will be held as constant. Okay, and uxx xt is equal to x double prime x t of t, because we hold the function t as constant. Okay, and then by substituting into the heat equation, both this one and this one in the heat equation here, we will have this one, utx of t equal to k u s x is x of x t prime equal to k s double prime t. Okay, so we are going to use the separation of variables. So we separate the variables x in one side and t on one side. So here it will be x double prime x double prime of x over x of x equal to t prime t over k t of t. Okay, remember k should be always gonna be on the side of t. Okay, for s there should be no constant. Okay, the constant should be on the side of t. Okay, this is what we call as the same as equal to p. Okay, so note that since s of x and t of t are independent, that means independent variables, it change, it varies. So this equation is true if each side is equal to the same constant p. That means if there is changes in t, there will also be changes in x, but x times t should always gonna be equal to p, the same constant, which is called separation constant. Okay, p here is called the separation constant. So equation 6 here will lead to two ODEs. The first one is from this part. Okay, going to use another color. Okay, x double prime x over x of x equal to p. We have x double prime x minus p as x equal to 0. And the second one would be this one. The blue one will be this. Okay, t prime t equal to pk t of t equal to 0, because we bring the denominator to the right. Okay, and there are three possibilities for the value of p, which means first p equal to 0. When p equal to 0, we will have this equation, right? So that means x double prime x equal to 0 and t prime t equal to 0. And solving these equations, we will get x of x equal to a1x plus a2 and t of t equal to a3. Because when we integrate, okay, integrate t prime t with respect to t, it will be because this one is actually equal to 0. So when we integrate, sorry, I think I should do it. Okay, there. When we integrate 0 with respect to t, we'll have a constant. Okay, that's why we put a3. Okay, for x prime x, that means when we integrate 0 with respect to x, it will be, sorry, I think it's going to be here, a1. Okay, and then next, when we integrate a1 with respect to x, it will be a1x plus a2. Okay, because when after we differentiate constant, we're going to get 0, right? That's why when we integrate 0, it will be constant. Okay, so here something that need to okay, that would correct. That means UST is equal to a1x plus a2 times a3. Okay, let's say p is greater than 0, and suppose that we use p equal to lambda squared. Okay, because it is positive, right? So lambda squared would be the positive value. So this would be the two new equations. Okay, solving these equations, we actually will get this one. Okay, s of x and t of t. This would be the UST. Okay, because we actually substitute m squared minus lambda squared equal to 0. And here you will have m squared equal to lambda squared, right? So therefore m is equal to plus minus lambda here. As you can see, exponent lambda x, exponent negative lambda x. And this one is t prime. It's going to be the review that I did using that is based on the first differential. Okay, because t prime is the first order, right? So please go back to that video if you have difficulty on understanding how it comes to this term. Okay, so this will be the UST. And the third one, we have P less than 0. So that means suppose that P is equal to negative lambda squared. Okay, so S double prime S equal to this one and T prime T is this. So solving these two equations, we get S of X equal to A1 cos lambda X plus A2 sin lambda X plus and T of T is equal to this one, A3 exponent negative K lambda squared T. So this would be the UST. Okay, the temperature. So we have to consider the solution which satisfies, okay, the given boundary conditions. Okay, for heat equation and for all equation, actually we will actually use this one. P is less than 0 because when we use P equal to negative lambda squared, it actually fulfills all the given boundary conditions. Okay, that's all for the introduction of heat equation. Thank you. Assalamualaikum.